earthquakes, earthquake simulations, earthquake dynamics, earthquake physics, things like that. One is called Virtual California. It's a series of faults in a model Earth, and we drive the faults, and we have some information about the physics of friction and what happens on those faults. And so what we do is we make synthetic earthquakes, simulated earthquakes on the faults. And so what we can do is look at long histories of those earthquakes on the model faults. Another thing we do, major thing we do, is earthquake forecasting. And that's done not only in a research sense, but also in a public outreach sense. We have a website, openhazards.com. AIP is going to do, has proposed to do actually a TV show on this. During the past 10 years, we've had something like 1 million people killed from earthquake disasters. That started in the Bhuj earthquake in India. It has, of course, continued with the Sumatra earthquake in 2004, on December 26th, the tsunami that killed almost 250,000 people in Sumatra, Indonesia, Thailand, Sri Lanka, and so forth. It's continued through the Wenchuan earthquake, the Pakistan earthquake. Probably 80,000 people were killed in the Pakistan earthquake in 2005, and in the Wenchuan earthquake, China, in 2008. And of course, now we've just seen the earthquake in Japan, which was a magnitude 9.0. It's kind of interesting if you look at the biggest earthquakes since 1900 AD. About 16 of the biggest 16 earthquakes, approximately 7 of them occurred. These are bigger than 8.5, magnitude 8.5, so they're really big earthquakes. About 7 or 8 of them, I can't remember the exact number, occurred between 1950 and 1965, and about 5 of them have occurred since 2007, from 2007 till now. So there were 3 events in Sumatra, the 9.1 or 2, and then 2 8.6 earthquakes, the northern and southern Sumatra earthquake, the Japan earthquake, and the Chile earthquake, magnitude 8.8 of February last year, February 23rd of last year. There was, of course, the Haiti earthquake as well, which was sort of not one of these huge earthquakes, but it happened in a place where the building construction was hideous, and 200,000 plus people died. I don't think we'll ever know exactly how many people died in that event. So it's an interesting question as to whether these things are actually correlated in time or not. Some people say yes, some people say no, but I think at this point the evidence is leaning in the direction that they are correlated in time or synchronized in time. We know from our studies of complex nonlinear systems that if you put Huygens, Christian Huygens observed this in 1640-ish AD, that if you put 2 pendulum clocks back to back on a wall and leave them there for a few hours, the pendulum will synchronize. And that's because of the interaction between the clocks. Well, earthquake faults are basically clocks also, in a sense. If you had an isolated earthquake fault driven at a constant rate, it would fail and have an earthquake every so often, every 100 years or so. On the San Andreas Fault in California, for example, we know that earthquake faults tend to be, the largest earthquakes tend to be separated by anywhere between 150 and 200 years. So they would be sort of analogs of clocks, but earthquake faults interact through the medium of the Earth, the elastic interactions in the Earth. And so there's every reason to think that you could get synchronization of the largest events, just like you get synchronization of these clocks. I talk about the California and Japan 4 cities forecast. So 4 cities in California, 4 cities in Japan, tracking what the probability of the earthquakes would be. And the 4 cities in California are San Diego, Los Angeles, San Francisco, and Sacramento. And the probability of a magnitude 7 earthquake within 150 miles of those cities within the next 12 months is typically about 10%, and I can't remember the exact figures. It was high prior to the Baja earthquake of April 4th of last year. It then fell off quite rapidly, but because of the large number of small earthquakes that occurred following that, the probabilities rose again quickly. Basically what we do is we count the number of small earthquakes since the last big earthquake. We know from the laws of seismology that there are a certain number of magnitude 3s, like typically 1,000, for every magnitude 6. So essentially if you sit there and you count magnitude 3s since the last 6 in the region of interest, by the time 1,000 magnitude 3s occur, you're about ready for another one. It's mature. Okay, so that's the way we do it. The magnitude 3s can be very unevenly spaced in time, of course, which is one of the reasons that earthquake forecasting is difficult. Also, the information is incomplete. But using those kinds of ideas, we can actually come up with a pretty decent probability estimate of what, how soon the next earthquake will be and where.